Welcome back. We'll do the last parts of this now. And so what we're going to consider is what happens if we apply our techniques to the general form. So y dash would become 2ax plus b, wouldn't it? So that would be our part there. Now solving for 0, y dash is equal to 0, would be solve algebraically 2ax plus b is equal to 0. That would be our solving part. So just a bit of undo. So minus b both sides. So 2ax would be equal to b. And dividing undo. Just do to one side, do to the other. And so what we can say is that x generally turns up, we think, as a max-min. That's generalizing. Of course we can't. We just demonstrated that we might need to check our intervals. But it can serve up a max-min. So we can check that algebraically when we've got our quadratics. It'll serve it up. Okay? Because a quadratic is only a single point, we call this one x vertex. And x vertex is a single point, so there'll always be 1 minus b over 2a. So we can't use this on other, but on quadratics we can. Okay? So if we go ahead and have a look at y double dash would be equal to 2a, wouldn't it? So that's how we would do that. If we were to set that as 0, or if we just think about what a would be. If a is positive, that's the way we write that in the maths language. If a is positive, then what we can expect is that y double dash is positive, which is concave up. So it goes with the positivity. And we say for all x. And we can say that only for the quadratic. Okay, for all x. And so that becomes a genuine concave up. Y double dash for our x critical. It'll be positive also. Which implies x represents the location of a min. Okay. Concave up. And I'm going to say it this way, everywhere. Concave up. Alright. Likewise, if a is negative, this implies that the second derivative is everywhere negative, which implies for all x, the second derivative at the critical value of x negative, which implies x critical is max. That is, y is everywhere concave up. Now that's only for the quadratics, so concave down. So it's only for the quadratics, okay? So it's a shortcut for us to use if we're doing some explanation of that. Alright, so what we can do then is have a look at this one. Now there's a little bit of complexity in the example because it's not an example of the square that we just did, but it's an example of a cube. So there's a little bit of work there for us to do. But y dash will be x squared, 3x squared minus 12x minus 15. And so we need to solve this quadratic. Look, I'm going to be a bit cheeky. I'm going to look at the roots of this as 5 and 9, plus or minus, but it's also plus or minus 3 and 15. Now actually I'm thinking that it's 3 and 15, not 5 and 9. 9, 10, 11, 12, 13, 14, it doesn't quite get me there. But 3 and 15, the difference is 12, isn't it? So grouping in pairs is a technique. You could use any of your techniques I've taught you. My favourite one is completing the square, and in that I'm doing this one. And I'm doing it because it's a non-monic. So basically what I'm going to do is rewrite the sum term, just leave all those there, and I'm going to have minus what is it going to be? 3 or 15? I think I'm going to have plus 3. I'm guessing plus 3x minus 15x minus 15. And you can see they kind of go together as a pair, and that's grouping in pairs. All right, so the solution of this is going to be, what can we take out that's common? 3x. And that'll leave us with x plus 1. Now we need x plus 1 to be in the other bracket, so hopefully I've chosen correctly. If not, it won't work. So I'll need to put a 15 out. Now that gives me 15x plus 15, but if I make it a minus, there's no problem. So this becomes 3x minus 15 in solution with x plus 1. And so we've found our solutions. Okay. Solving. I didn't put the solving up, did I? I was a bit naughty. Taking shortcuts, oh no. So therefore x, when is this true? Well, when x is minus 1. And when 3x minus 15 is 0, so 3x would have to be plus 15, so x has got to be 5. So at those two values, we're expecting to find m equals 0 at those two values. Okay. Now what I'm going to do is go straight to the second derivative and check the second derivative. So it'll be 6x squared, 6x minus 12. I'm going to check the concavity of our 2 points to see if they're the same or different. So we've got 6 minus 1 and minus 12. So we get minus 6 minus 12 is minus 6 minus 12, which is minus 18, the emphasis being on 18. So for this particular point of negative 1, it's concave down. Let's check the second derivative at 5. You'll notice I haven't checked the y values. I haven't found the y coordinates. Minus 12. So 30 minus 12 is a big positive. Is 18, but it's plus 18. So that's a smiley face. All right, do we have enough? Well, it'd be nice if I had the y values here. So y minus 1. So there's a bit of computation needed. y5. There's a bit of computation needed. So 5 is like minus 104, so it's quite a long way down. Minus 1 is 4, I believe. So we'll do this way. Put a bit of a break in here. And we'll put minus 104 down here. We'll put our values across. So 5 minus 1 and 4. So we know there's a dit at that point. And 1, 2, 3. So 4 would be square 5's here. So we know that down at this point here, there's this one, but we know more than that because of the second derivative. The first derivative is -1. It's concave down, so it's going like this. We'll just put -4 over here. So it's going to be concave down. And this one here is going to be concave up. Now, the next thing we want to do is just check the second derivative set to 0. So we plus 12, so a bit of working. So plus 12, 12 divided by 2. 12 divided by 6, I said it, you see. 12 divided by 6 is 2. So at x equals 2, 4, which is a bit here. That one might be a bit wide. And 2 down at -50. There's a point of inflection. So we might have to just rescale a little bit here because my scales are a little bit out. And we go ahead and draw this. We're coming through -4, so my vertical scale is not the same clearly. But the idea is that there's a concavity change. So that's swooping down this point here. It's not quite right, Jason. So I'll tell you what I'm going to do to get this right. I'm just going to fix this up. It's better that it's fixed up than not. So let me just get all that out of the way. So it's quite a biased curve because of the length. So we know we're just going to go up to 4 only. So we're just going to do this. Make that 4. So that would be 4. So this will be -1. So that will be the value. Now 4, 5. Now this is where we can get ridiculous. We can break it. Let's break it nice and early. Okay, and then we can get 50 and 104. So let's do -104 -50. The other point we had was 2. So we get our point of inflection here, and we get our, so we get these all happening. Now 4 is going to be same distance here. So that's our polynomial y-intercept. Alright, so we get a nice swoop up down to this point here. So we get that 4. I just wish I'd had that up a little bit further. So we're going to get a swoop down. No, it just doesn't look right still, does it? Got to get that in. Sorry, I'm going to have to just do it this way. Sorry, it's more about my handwriting than it is anything else at this point. So I want a big concave stretch. It's just too close, isn't it? The horizontal scale needs to be bigger. What about that, folks? I'm okay with it because I'm doing it by hand. I'm not using graph paper because of the offset value of 104. So it'll teach me to have such a big value. So we're going to have a lovely swoop down to a point of inflection and a lovely swoop the opposite direction. This point of inflection is then going to swing down nice and deeply to a min, and then it'll start to swing up like that. Alright, so we've got our values that we can put in, just exaggerating the scale. Okay, and the 4. So I'll extend that up a bit more, if only for the scale. So if our -4 is here, we're going to have our positives across this way. Alright, that's a bit more proportionate. Alright, sorry about the delivery on that, it took a little bit. And -1, because that's way out of scale. So this point of inflection is -50. And it's -104. So it's a bit hard because they're so long on the tail there. Alright, but that gives you a sense of where the various parts are. Okay, and that was 2, wasn't it? So we're able to complete pretty much all of that information. Now we can go through and check the single derivatives, but other than that, I think we're done. Alright, so finally, just a revision of all the bits and pieces put together. So I think the previous lecturer did that, so credit for that. But I'll let you use all of that to address the applications and tutorial questions. Thanks very much.